Hi everyone, welcome back. Next we're going to look at local and global wind patterns. So first we're going to start with local wind patterns, which are caused by differences in pressure at very small scales. And so if you are at the beach in the afternoon, which way is that wind blowing, right? In the afternoon we have a sea breeze, right? So if you're at the beach in the afternoon, that wind is blowing from off the ocean. And again, that's because of a difference in heating, which creates a difference in air pressure, which creates that wind. But these can help us understand global wind patterns much better. And so we're going to talk about convection loops. We talked about convection heating in last chapter, but here is an example. I'm going to run through this with you. But here we have an island in the sun, right? So here's our little island, lots of sun, no clouds interfering with us. And so this island is going to heat up more quickly than the water around it. And this is going to cause warm air to rise off of this island. This is going to create a pressure gradient at altitude. So you're going to have higher pressure above the island and lower pressure above the ocean from this uneven heating and this warm air rising. So again, because of this difference in pressure, you're going to have air flowing from high to low. So again, air is going to rise up and then be pushed out and want to go over to the area of low pressure. And then as it gets to that area of low pressure, this air has cooled after it has risen. So the air begins to sink, resulting in higher pressure over the water. Where'd my cursor go? So now you have higher pressure over the water. And then the surface pressure gradient develops and the air blows back to the island. So you wind up getting these convection loops. We see these at very small scales, and we also see them at very, very large scales. But this is one of the reasons why you get these sea breezes and land breezes, right? We have differences in pressure, uneven heating. So you're going to have, during the day, you're going to have that breeze blowing from the sea onto the land, and it is going to reverse at night. So at night, pressure patterns are reversed from the daytime. We also tend to have no breeze in mid-morning or early afternoon, and that's because those are moments when those pressures are actually equal because you have they have kind of heated to the same place. When we think about pressure and elevation, pressure always decreases with elevation, no matter what. High pressure, though, in the upper atmosphere refers to a relative high pressure. And so that means the pressure there is lower than the pressure near the surface below it, but much higher than other areas at the same high elevation, right? So when we're looking at high pressure in the upper atmosphere, we're talking about high in relation to other areas of the upper atmosphere. But the upper atmosphere is always going to have lower pressure than the lower atmosphere. And so global wind patterns are driven by these convection loops, and they kind of wrap around the planet. The big ones right here are called Hadley cells. We get this heating that happens at the equator. Warm air rises, and we get that same effect that we saw on a much smaller scale for that island. So again, I'm going to run through how these Hadley cells work. But basically, you get warm air. Here's number one. That's going to rise near the equator. It leaves a band of low pressure at the surface. So again, this warm air is going up. So you have this kind of this loss of air pressure that's happening right there. That creates the something called the Intertropical Convergence Zone, which is called the ITCZ, which is visible as a band of clouds. And we'll look at some satellite imagery of that in a minute. Then, as a result of this air rising, you get high pressure in the upper atmosphere at the top of the troposphere right here. You get winds that blow from the equator towards the poles from the upper atmosphere. Again, we're going to get that same circling effect that we saw at that island. So here you have, these are called the anti-trade winds, the ones that happen in the upper atmosphere, right? So air is coming up from the equator and being pushed out along these anti-trade winds. And then because the air has risen up, it's going to start to cool and sink back down, usually at about 30 degrees north and south latitude, respectively. And this leaves a band of high pressure at the surface. And so you get these subtropical highs right here. So areas of high pressure. So we have an area of low pressure here, an area of high pressure here, an area of high pressure here. And finally, 5, that surface wind is going to blow this way, and these are called the trade winds. These are pretty consistent winds. Hawaii gets affected by the trade winds, but these are surface winds that blow from these subtropical highs back to that low pressure ITCZ. And again, those are called the trade winds. So a couple things to remember from this slide. The Intertropical Convergence Zone, or ITCZ, which I'll refer to it for the rest of the lecture, is that band of clouds that is forming from that warm air rising near the equator. The anti-trade winds are the winds in the upper atmosphere pushing away from the ITCZ. You're going to get a subtropical high at about 30 degrees north and 30 degrees south. And then finally, those trade winds that are coming back closer to the surface. And so Hadley cells are three-dimensional, and they wrap around the entire planet. You have these alternating bands of high and low pressure. And so this is a satellite imagery of the ITCZ. Your subtropical high is over here pushing your trade winds towards the ITCZ, and it's visible as a band of clouds. We'll look at a couple pictures of it. And so a quick climate lesson here, when you have high pressure, you're generally having dry conditions, and when you have low pressure, you're having wet conditions. And when we think about that intuitively, places on the equator tend to get a lot of rain, right? You get this, this low pressure, all the air is being sucked up, clouds are being created, and you're getting a lot of rain. Right, and so you look here as an average rainfall chart. This is for 30 days in July, but you can see here lots of precipitation. Here is your ITCZ right here. That's going across the planet, and you're going to get lots and lots of precipitation from it. And so this whole system shifts with the seasons, right? And so where do you notice the ITCZ in this picture? The red line here is our equator, and you can notice that band of clouds that's happening just south of the equator. And so why is it located south of the equator? It's located south of the equator because this is where is getting the most insolation at that time. And so what time of year? This means that it is summer south of the equator. So this is probably December or January, right? And this whole thing switches back and forth. And so that ITCZ will move back and forth depending on the seasons. And you get this, this is in Africa. You have these grasslands here that kind of move back and forth based upon how much precipitation it's getting and where the ITCZ is. And here we can look at pressure patterns in the ITCZ. So this is in July. That ITCZ is going to be in the northern hemisphere. So here's the equator, our 0 degrees. It's going to be up above that equator. It's not a perfect band around because it interacts with a bunch of other variables, but it's going to be in the northern hemisphere in July. And in January, when the southern hemisphere is having their summer, it's going to be south of the equator. It's always going to be in the tropics, though. And so here you can see that going back and forth, that seasonal change between January and July. So again, we're getting these alternating highs and lows. We have that low pressure near the equator. We had subtropical highs. We also have polar highs. Extreme cold causes extreme high pressure at the surface of the poles. And so you have a permanent anticyclone over Antarctica. And remember, Antarctica is a desert. It's not actually getting precipitation there. It's just frozen. So again, the poles we want to remember are always areas of high pressure. Near the equator is always an area of low pressure. There's a slightly different pattern over the Arctic, and that has to do with how much land there is there. Um, So you're going to get this high pressure over Siberia in the winter, which is in northern Russia. And it's going to be much weaker in the summer. So we have polar highs, but then alternating from that, south of it, we're going to get subpolar lows. And remember, lows, generally, we're talking about rain. So we have winds converging from these polar highs or easterlies, and these subtropical highs or westerlies. They are converging together. You have an area of low pressure. We can see here, like, that's near our Pacific Northwest, which is very, very, very rainy. So mid-latitude areas around 50 degrees, such as Seattle and New England and Old England, here you're again in that subpolar low, you're going to get a lot of precipitation. And so this is in January during the Northern Hemisphere's winter, where they're going to get a lot of precipitation, and it's going to happen in reverse in the Southern Hemisphere. The polar front is the boundary between that warm and cold air, and it's very, very rainy and very windy. And if any of you have visited the Pacific Northwest or Seattle, or if you're from there, you can attest to it. So again, we're getting these alternating highs and lows. Polar high, subpolar low, subtropical high. The ITCZ is an equatorial low, high, low, high. So low pressure creates convergence, which you have this air coming together and then rising. And so you get rainy areas near the equator. Here are those clouds rising up. And then you also get them at the mid latitudes right there. High pressure creates divergence, dry conditions around 30 degrees. Where's my cursor? Right here, and at the poles. And so we can see, right, here's that subtropical high right through the Sahara Desert, right through the Middle East. Not a lot of precipitation happening there. And so land and water differences also affect global wind patterns. Again, land and water heat up differently, which we've learned. And differences in heating cause differences in pressure, which we've also learned, right? And so the monsoons are these very special rains that happen in several areas, but are very, very important in parts of Asia and India. So you get these continental areas that are heating up in the summer in Siberia and China, and the ITCZ gets pulled inland because of this heating. And it sucks all of this warm, moist air from the Indian Ocean towards India. And it gets very, very rainy and very predictably rainy, but it's a ton of rain that happens very, very quickly. And you're going to watch a couple of videos about the monsoons in India after you finish this part of the chapter that you'll use for your final exercise. Those continental areas get very, very cold in the winter. You have this high pressure, the Siberian high, and so it blows cool, dry air towards India. So you're getting not very much precipitation, then almost no rain. It's not unique to South Asia, but it is most prominent there. And so monsoons, especially in India, are vital to agriculture. People wait for the monsoons. They grow specific crops that are very dependent upon the monsoons. And when they do not come in the amount expected or at the time expected, it can really wreak havoc with agriculture. You're dealing with farmers that many of them, for the most part, have no irrigation system, and they are reliant completely on this monsoon season. One of the last things I'm going to talk about in this chapter is the Santa Ana winds, which we know very, very well in San Diego. We get these very hot, dry winds certain times of the year. that make it pretty uncomfortable to be in San Diego when they happen. But what happens is you get this very strong high pressure system over this area is called the Great Basin. And so you get wind blowing towards the ITCZ. It goes southwest. So you have this area of high pressure. There's lower pressure over here, so that air wants to rush out of the high pressure. And then the air also heats up as it descends down the Sierra Nevada. And so this air gets channeled and gets even hotter as it makes its way through the Sierra Nevada. And so these usually happen in late summer and early fall. We are very susceptible to wildfires when they happen. It dries out the air so much, there's very, very little humidity, and it can make things quite dangerous. And the last thing I'm going to talk about is El Nino, which I'm sure many of you heard about. We are coming out of an El Nino. We had one last year. And so basically, El Nino is there is cold water and high pressure off of the coast of South America normally. So here is South America. You have this cold water that's usually here, and so you get this wetter conditions. In El Nino, you get this warm water that accumulates from the Western Pacific, and it disrupts the pressure patterns. And so the wind patterns change dramatically, and usually we result in a lot more rain. This past rainy season that we had was not an El Nino, it was the year before. But precipitation patterns change. Fish also move around a lot, so it can really wreak havoc with fisheries. But generally speaking, during an El Nino, we get wetter in California. We had one of these in the 2015-2016 year, and they thought it was going to be a very, very severe El Nino, and it wound up being a pretty mild one. But they tend to run about every 7 to 13 years. But one of the worries of climate change is that it's going to change the patterns of El Nino. And so I lied. There's one more thing we're going to talk about. Winds in the upper atmosphere, right? Because both the winds that we're talking about that are affect us are in the lower atmosphere. But generally speaking, in the upper atmosphere, besides these Hadley cells that we talked about, you're getting a general wind pattern in the upper atmosphere from west to east. These are the anti-trade winds, and they are the opposite of the trade winds again. And this is what creates our jet streams, which is the flow of air between the boundaries of these Hadley cells, right? And so we get polar jet streams. So you get this low pressure in the upper atmosphere above the poles, this very, very cold air, high pressure in the upper atmosphere above the mid-latitudes again. And so this air flows along the boundary between warm and cold, pushing things from west to east. And so combined with the surface westerlies, the weather moves from west to east in the United States. And again, I mentioned previously that I grew up on the East Coast of the United States. We would look to the Midwest to see what the weather was there because it was eventually going to come our way. So changing temperature patterns mean changing pressure patterns. So the jet stream alters course with changing pressure. Rossby waves are these kinks that happen in the jet stream right here, right? They don't flow, but they flow around these areas of high and low pressure. So when you have an area of high pressure that's pushed up here, the jet stream is going to curl around this high pressure, then curl around. It's going to drag cold air from Alaska and from farther north and bring it down, and you're going to get this cold that happens. And so the East Coast was plagued a couple of years ago by something called the polar vortex. And I happened to be back east during an episode of that, and the temperatures were around 7 degrees. So it happens more frequently when there's differences in temperature between the poles. It happens more frequently when differences in temperature between the poles and the tropics are smaller. And so that is the end of chapter 5. You're going to proceed on to your last exercise and do your weekly journal and your quiz, and that will be it for module 2.